Assalamualaikum warahmatullahi ta'ala wabarakatuh.
I'm Asmin Abdullah.
And I'm Laika Alimpang.
And Norain Haji Salib.
And now in this video, we're gonna talk about the volcanoes and Plutons.
Guys, so I'm Laika Alimpang. So now I'm going to discuss about magma. So what is magma? So magma is found inside the volcano and also known as magma is a molten rock. Magma forms in the magma chamber of a volcano, and a conclusion magma forms by increasing temperature and decreasing pressure and also adding water. So increasing temperatures, everyone knows that the solid melts when it becomes hot enough. For example, the butter melts in frying pan and the snow melts under the spring sun. For similar reasons, an increase in temperature will melt a hot rock. Undoubtedly, however, increasing temperature is the less important cause of magma formation in the asthenosphere. And also the decreasing pressure. A mineral is a solid composed of an orderly array of atoms bounded together. When a mineral melts, the atoms become disordered and move freely, taking up more space than the solid mineral. Consequently, magma occupies about 10% more volume than the rocks that melt from it. If a rock is heated to its melting point on Earth's surface, it melts readily because there is little pressure to keep it from expanding. The temperature in the asthenosphere is hot enough to melt rock, but the high pressure prevents the rock from expanding, so it does not melt. However, in the pressure were to decrease, large volumes of asthenosphere rocks would melt. Melting caused by decreasing pressures is called pressure release melting. In the section Environments of Magma Formation, we will see how certain tectonic processes decrease pressure on asthenospheres rocks, terribly melting them. And also, the process that forms magma is the adding of water. A rock contains small amount of water, generally melt at a lower temperature than an otherwise identically dry cook. Consequently, addition of water to rock that is near its melting temperature can melt the rock. Certain tectonic processes described shortly add water to the hot rock of the asthenosphere to form magma. The other one is about environments of magma formation. Magma forms abundantly in three tectonic environments. Number 1 is spreading centers. Number 2 is mantle plumes and subduction zones. Let us consider each environment to see how rising temperature, decreasing pressure, and adding of water can melt the asthenosphere to create magma. Magma production in spreading center. As a lithospheric plates separate at a spreading center, hot plastic asthenosphere oozes upward to fill the gap. As the asthenosphere rises, pressure drops and pressure release, melting forms basaltic magma. The term basaltic and granitic refer to magmas with the chemical composition of basalt and granite respectively, because the magma is of lower density than the surrounding rock. It rises buoyantly towards the surface. Most of the world spreading center lie in the ocean basins where they form the mid-oceanic ridge sit. The magma created at the spreading centers erupts from the ridge beneath the sea and solidifies to form new oceanic crust. The oceanic crust then spread outward, riding atop the separating tectonic plates. Nearly all the Earth's oceanic crust is created in this way at the mid-oceanic ridge system. In most places, the ridge lies beneath the sea. In a few places, such as Iceland, the ridge rises above sea level and volcanic eruptions are common. Some spreading center, like the East Africa Rift, occur in continents, and here, two basaltic magma erupts into Earth's surface. And the other one is the magma production in a mantle plume. Recall from chapter 6 that a mantle plume is a rising column of hot plastic rock that originates deep within the mantle. The plume rises because it is hotter than the surrounding mantle and consequently is less dense and more buoyant. As a plume rises, pressure release, melting just beneath the lithosphere forms magma, which then rises toward Earth's surface. Because mantle plumes and hot spots form below the lithosphere, hot spots usually occur within tectonic plates rather than at a boundary. For example, the Yellowstone hotspot, responsible for the volcanoes and hot springs in Yellowstone National Park, lies far from the nearest plate boundary. A mantle plume rises beneath the sea. Volcanic eruptions build submarine volcanoes and volcanic islands. The Hawaiian Islands are a chain of hotspot volcanoes that form over a long live mantle plume beneath the Pacific Ocean. And the other one is the magma production in the subduction zones. In subduction zones, addition of water, decreasing pressure, and heat from friction all combine to form high quantities of magma. As you learn in chapter 6, a subducting plate is covered by water-saturated oceanic crust as the wet rock dives into the hot mantle. Rising temperature vaporizes the water, forming vapor that ascends into the hot asthenosphere directly above the sinking plate. And also, we have a three-process melt the asthenosphere to form magma at a subduction zones. Number 1 is the steam rises from wet rock oceanic crust on top of the subducting plate. And the number 2 is circulating into asthenosphere decreases pressure on hot mantle rock. And last one is the friction hits rocks in the subduction zones. Addition of water is probably the most important factor producing melting and in a subduction zone, and frictional heating is the less important. Volcanoes and plutonic rocks are common features of a subduction zone. The volcanoes of the Pacific Northwest, the granite cliffs of Yosemite, and the Andes Mountains are all example of volcanic and plutonic rocks, form at the subduction zones. The Ring of the Fire is a zone of active volcanoes that traces the subduction zones encircling the Pacific Ocean Basin. About 75% of Earth's active volcanoes, exclusive of the submarine volcanoes at the mid-oceanic range, lie in the Ring of the Fire. The last one is basalt and granite. One of the planet Earth is the composition of the crust of the Earth. There are in fact two kinds of crust. There are oceanic crust, which is underlying the oceanics in the world, and there is continental crust. These kinds of rocks both are igneous rock in origin is fire-formed rocks, and yet they different in their composition, the kind of mineral they are made of, and they differ in their density. Different in that way, they also different in age. The basic underlying rock of the continents is much older than the rock of the oceanic crust. The continental crust that we describe them as being granitic and in composition, granite, this kind of rock. Here is the granitic composition rock. On the other side, the rocks of the oceanic crust are described as basalt, and this is one example of basalt lava rock. Of us would probably recognize and describe it. These rocks are quite different in appearance. This characteristic of continental crust, this of oceanic crust. If you look at the granite, you see that it is very grainy. You can see black peaks in it, biotite and quartz. The white, but you see large grains in the rock. This one of the grains are somewhat larger than in this one, but the grains are there in the both cases. However, when you look at that basalt characteristic of the oceanic crust.
Hi guys, I am Asmin Abdullah. In this part of the video, I'm gonna talk about magma behavior, plutons, and volcanoes. Magma behavior. Once magma forms, it rises toward Earth's surface because it is less than surrounding rock. As it rises, two changes occur. 1. Magma cools as it enters shallower and colder levels of Earth. And 2. Pressure drops because the weight of overlying rock decreases. Cooling tends to solidify magma, but decreasing pressure tends to keep it liquid. So, does magma solidify or remain liquid as it rises toward Earth's surface? The answer depends on the type of magma. Basaltic magma commonly remains liquid and rises to the surface to erupt from a volcano or flow onto the sea floor at the mid-oceanic ridge. In contrast, granitic magma usually solidifies within the crust. And the silicate minerals, silicate tetrahedral link together to form the chins, sheets, and framework structures. Silicate tetrahedral link together in a similar manner in magma. They form long chins and similar structures if silica is abundant in the magma, but shorter chins if less silica is present. Because of its higher silica content, granitic magma contains longer chins than does basaltic magma. The long chins become tangled making the magma stiffened or viscous. It rises slowly because of its viscosity and has ample time to solidify within the crust before reaching the surface. In contrast, basaltic magma, with its shorter silicate chins, is less viscous and flows easily. Because of its fluidity, it rises rapidly to erupt off Earth's surface. Second, and more important, difference between the two magmas is that granitic magma contains more water than basaltic magma does. Water lowers the temperature at which magma solidifies. If dry granitic magma solidifies at 700 degrees Celsius, the same magma with 10% water may not become solid until the temperature drops below 600 degrees Celsius. Water tends to escape as steam from hot magma, but deep in the crust, where granitic magma forms, high pressure prevents the water from escaping. As the magma rises, pressure decreases and water escapes. Because the magma loses water, its solidification temperature rises, causing it to crystallize. Water loss causes rising granitic magma to solidify within the crust. Because basaltic magmas have only 1 to 2% water to begin with, water loss is relatively unimportant. As a result, rising basaltic magma usually remains liquid all the way to Earth's surface, and basalt volcanoes are common. In most cases, granitic magma solidifies within Earth's continental crust to form a large mass of igneous rock called a pluton. Many granite plutons measure tens of kilometers in diameter. How can such a large mass of viscous magma rise through solid rock? If you place oil and water in a jar, screw the lid on, and shake the jar, oil droplets disperse throughout the water. When you set the jar down, the droplets coalesce to form larger bubbles, which rise toward the surface, easily displacing the water as they ascend. Granitic magma rises in a similar way, except that the process is slower because it rises through solid rock. Granitic magma forms near the base of continental crust, where surrounding rock is hot and plastic. As the magma rises, it pushes aside the plastic country rock, which then slowly flows back to fill in behind the rising bubble. After a pluton forms, tectonic forces may push that part of the crust upward, and erosion may expose parts of the pluton at Earth's surface. Batholite is a pluton exposed over more than 100 square kilometers of Earth's surface. An average batholite is about 10 kilometers thick, although a large one may be 20 kilometers thick. Stack is similar to a batholite but is exposed over less than 100 square kilometers. Batholite is commonly composed of numerous smaller plutons untrodden sequentially over millions of years. A volcano is a hill or mountain formed from lava and rock fragments ejected through a volcanic vent. The material erupted from volcanoes creates a wide variety of rocks and landforms, including lava, plateaus, and several types of volcanic outlets. Many islands, including the Hawaiian Islands, Iceland, and most islands of the southwestern Pacific Ocean were built entirely by volcanic eruptions. Lava is magma that flows onto Earth's surface. The word also describes the rock that forms when the magma solidifies. Lava with low viscosity may continue to flow as it cools and stiffens, forming small, glassy surfaced, wrinkled or roughy ridges. This type of lava is called pohoyhoy, from the Hawaiian meaning smooth or polished. If the viscosity of lava is higher, its surface may partially solidify as it flows. The solid crust breaks up as the deeper. Molten lava continues to move, forming a lava with a jagged, rubbled, broken surface. When lava cools, stiffening gases such as water and carbon dioxide form bubbles in the lava. If the lava solidifies before the gas escapes, the bubbles are preserved as holes in the rock called vesicles. The gentle-less type of volcanic eruption occurs when magma is so fluid that it ooze from cracks in the land surface called fissures and flows over the land like water. Fissures and fissure eruptions vary greatly in scale. In some cases, lava pours from small cracks on the flank of a volcano. Fissure flows of this type are common on Hawaiian and Icelandic volcanoes. In other cases, however, fissures extend for tens or hundreds of kilometers and pour thousands of cubic kilometers of basaltic lava onto Earth's surface. A fissure eruptions of this type creates a flood basin, which covers the landscape like a flood. It is common for many such fissure eruptions to occur in rapid succession and to create a lava plateau or basalt plateau. Volcano types. Volcanoes differ widely in shape, structure, and size. Lava and rock fragments commonly erupt from an opening called a vent, located in a crater, a bowl-like depression at the summit of the volcano that was itself created by volcanic activity. Shield volcanoes, one of the volcano types. Fluid basaltic magma often builds a gently sloping mountain called a shield volcano. The sides of a shield volcano generally slope away from the vent at angles between 6 degrees and 12 degrees from horizontal, although their slopes are gentle. Shield volcanoes can be enormous. The height of Mauna Kea volcano in Hawaii, measured from its true base on the sea floor to its top, exceeds the height of Mount Everest. Although shield volcanoes, such as those of Hawaii and Iceland, erupt regularly, the eruptions are normally gentle and rarely life-threatening. Lava flows occasionally overrun homes and villages, but the flows advance slowly enough to give people time to evacuate. Cinder cones, the second types of volcano. Cinder cone is a small volcano composed of pyroclastic fragments. A cinder cone forms when large amounts of gas accumulate in a rising magma. When the gas pressure builds sufficiently, the entire mass erupts explosively, hurling cinders, ash, and molten magma into the air. The particles then fall back around the vent to accumulate as a small mountain of pyroclastic debris. A cinder cone is usually active for only a short time because once the gas escapes, the driving force behind the eruption is gone. Composite cones. Composite cone, sometimes called a stratovolcano, forms over a long period of time as a sequence of lava flows and pyroclastic eruptions. The hard lava covers the loss of pyroclastic material and protects it from erosion. Many of the highest mountains of the Andes and some of the most spectacular mountains of western North America are composite cones.
Hello guys, good morning, good morning, good morning. By the way, I'm Noreen Haji Salek from BS Islamic Education. Guys, are you ready to listen? Now, we are going to discuss about volcanic explosion.
So, granitic magma solidifies within the crust. Under certain conditions, it rises to Earth's surface, where it erupts violently. Granitic magmas that rise to the surface contain only a few percent water, like basaltic magma. But decreasing pressure allows the small amount of dissolved water in granitic magmas to form a frothy, pressurized mixture of gas and liquid magma that may be as hot as 900 degrees Celsius. Volcanoes erupt when a molten rock called magma rises to the surface. Magma is formed when the Earth's mantle melts. If magma is thick, gas bubbles cannot easily escape and pressure builds up as the magma rises. When the pressure is too much, an explosive eruption can happen, which can be dangerous and destructive. So, ash flows. So, we have two types of volcanic activity. First, ash flows. Second, calderas. When we say ash flows, ash flow, a mixture of volcanic ash, large pyroclastic particles, and gas that flows rapidly along Earth as a result of an explosive volcanic eruption. When much of the gas has escaped from the upper layers of magma, the eruption ends. The airborne column of ash, rock, and gas then falls back to Earth's surface, spreading over the land and rushing down extreme valleys. So, second is calderas. Calderas, after the gas-charged magma cracks, the roof of the magma chamber collapses into the space that the magma had filled. Because most magma bodies are circular, when viewed from above, the collapsing roof forms a circular depression called caldera. Caldera collapse is usually triggered by the emptying of the magma chamber beneath the volcano. As the result of a large volcanic eruption, if enough magma is erupted, the emptied chamber will not be able to support the weight of the volcanic edifice above. Fractures will form around the edge of the chamber, usually in a roughly circular shape. These ring fractures may in fact serve as a volcanic vents. As the magma chamber empties, the center of the volcanic within the ring fractures begins to collapse. The collapse may occur as the result of a single massive eruption, or it may occur in stage as the result of a series of eruptions. The total amount of collapse may be hundreds or thousands of meters. So, when granitic magma rises to within a few kilometers of Earth's surface, it stretches and fractures overlying rock. Gas separates from the magma and rises to the upper part of the magma body. The gas-rich magma explodes through fractures, raising a vertical column of hot ash. Rock fragments and gas is used up the column collapse and spreads outward as a high-spread ash flow. Because so much materials has erupted from the top of the magma chamber, the roof collapsed to form a caldera. So, predicting volcanic eruptions, it is the major known volcanic disasters since the year 1,500 years. The potential for such disaster in the future makes a volcanic eruption one of the greatest of geologic hazard. It also makes risk assessment and prediction of volcanic eruption an important part of modern science. So, volcanic eruptions and global climate. We have learned that magma productions that the first step in the development of a volcanic eruption occurs in the upper mantle. However, as another example of system interaction, and eruptions can profoundly affect the atmosphere, climate, and living organisms. The gases and dust particles thrown into the atmosphere during volcanic eruptions have influence on climate. Most of the particles spewed from volcanoes cool the planet by shedding incoming solar radiation. The cooling effect can last for months to 2 years depending on the characteristics of eruption.
Thank you for watching. We hope you gain more knowledge in this video.
Then don't forget to subscribe.
Like and share.
If you have a comment,
Comment down below. Bye-bye.